Thank you so much. I'm extremely pleased to be here today. I really would love to thank Viviane Kassam. I'm very appreciative of the opportunity to come, and also to thank the EBRI and Brain Circle Italia. And I will just say that I too find the words of Rita Levi-Montalcini to be very inspirational. And I'll also thank, I think, a long history of neuroscience in Italy that was certainly an inspiration to me when I first began my degree in Montreal, because I was very interested in neuroanatomy and in also the brain structures that are related to movement. And that's something that Italian neuroscience has really brought to the fore. So what I would like to talk to you about today is a concept that we call musical groove. And I want to ask the question, why does listening to a rhythm make us want to move? So I thought we should have an example of this kind of music from one of the students in my lab who is part of a Brazilian drumming group. So if I can have this music, I think this will get us all moving. Definitely feel that you would like to move along, and especially, in just a moment, we're going to get this really nice drum break, right? That you can hear, and if you weren't stuck in your seats, you would be able to dance along too, right? So what is it? What is happening in our brain that makes us want to move to this kind of music? And it's not just this kind of clearly rhythmic music. We can hear this kind of sensation or feel this sensation of wanting to move when we listen to something like this beautifully played sarabande that we just had. So I'd like to talk to you about the idea that what makes us want to move and what gives us that pleasure when we listen to this kind of music is something about predictions. Our brain making predictions about what is going to happen next in the music. So when we listen to a piece of music, we're constantly making predictions. We're making predictions about what is going to happen, what's the next pitch that we're going to hear, and we're also making predictions about when it's going to happen. When is that next note going to happen? And what I think, is that when we try to make a prediction about when is something going to happen, we make a prediction using our body, using movement, even if we don't actually move. And I'll also try to convince you, or I won't convince you, but I think that our experience of these predictions is built, sort of like what Mirav was talking about, on our experience of music in our culture. So we hear music all around us, and when we hear that music, we acquire a sample. We hear lots of different kinds of music, and this allows us to make predictions about both that what and that when, and the kinds of predictions that we're able to make depend on the kind of music that we hear. So if I'm not familiar with a particular type of music, I'll probably be less accurate, less able to make a prediction about what's happening in that music. And one of the things that we think is that there is a tension between our ability to make a prediction, how accurately we can make that prediction, and what really happens in the music that drives pleasure and movement. So if music is too predictable, if we know exactly what's going to happen, like a children's song, we don't find that very exciting. We don't find that very enjoyable. And it yields no surprise. It yields no learning. So we enjoy it less. Surprise is important because if we hear something new, it doesn't fit with what we've heard before. We want to learn more about it. it has an intrinsic rewarding property. Learning is inherently rewarding, as I just said, and so for many different kinds of art, I think as we saw before, you also showed for memory, there's kind of a sweet spot where some sort of complexity, surprise, yields learning and yields pleasure. So I'll go on to kind of try to tell you a little bit more about this in detail. But first I'm going to tell you about the brain. Why might we engage both the motor system and this reward or pleasure system when we're listening to music that makes us want to move? So first, there are pathways that link the auditory regions of the brain here, conveniently located right above your ears, to both the frontal lobe and to motor regions of the brain. And this pathway that goes from auditory system to frontal is very important for these what or pitch predictions. And this dorsal pathway that goes from auditory cortex to the parietal lobe to motor and motor association regions of the brain is very important for timing. So there's a link between timing, between when something's going to happen and movement. There are another set of structures that are linked in to these cortical motor regions that come from the basal ganglia. And the basal ganglia can be broken up into at least 3 major systems. The first emanates from the putamen here that is linked to these motor cortical regions and is important, we think, for movement prediction and movement initiation. There's another stream from the caudate that's important for making higher order predictions. So when I have a musical rhythm, I don't have necessarily a completely regular, entirely predictable pattern of sounds. I have an idea of a global musical or rhythmic structure, and that may be something that is housed in the frontal lobe, and it's this link between the caudate and the frontal cortex that may be important for these higher order predictions. And then finally, very importantly, we have the ventral striatum, which is linked to the frontal cortex, and in particular, the orbital frontal cortex that Mirav brought up, and this is important for reward predictions. There's also another system that's quite important that is very near and dear to my heart, which is the cerebellum. We'll talk less about this today, but we think that this is important for generating these models and for evaluating error. So how do these brain systems work together to help us make these predictions in time? So some of this research really started quite a while ago with one of my students, Joyce Chen, who is now a professor at the University of Toronto. And what we did is we were interested in looking at what regions of the brain were engaged when you listened to and then reproduced musical rhythms. So what she did is she created a set of rhythms that varied in how complex they were, how rhythmically easy they were to reproduce. And she had people listen to them and then listen to them again and try to tap along in time with them. So I'm going to give you the opportunity to do Joyce's task. I'll ask you to play the very first rhythm. Okay, so there's the rhythm. You're going to hear it again. So if you imagined yourself trying to tap along with that, that was reasonably perhaps easy to do. But if I play you one of the second one, if you can play that. So this is a bit more difficult to tap along to. So what she had people do, as I said, is you listen, then you hear it again, and you try to tap along. And at the same time, we measured activity in the brain while people were doing this task. And what we found is if we look at the regions of the brain that are active when you're tapping along to those rhythms, you can see these motor cortical regions, the premotor cortex, the supplementary motor area, but also the basal ganglia, so those subcortical regions, and the cerebellum. So this is perhaps not surprising, right? You've listened to these rhythms, and now you're listening to them, and you're moving. So we asked a second question, well, what is happening when you listen to that rhythm, but before you tap along with it? So this is listening, and then you're anticipating. You know you're going to have to tap along with them next. So what regions of the brain are engaged when you're listening and preparing? And we see, again, these motor cortical regions and the cerebellum. We don't see the basal ganglia here, perhaps because you're not actually initiating a movement. Now, this was really exciting to us to see these motor regions engaged even when people weren't making a movement. But of course, you guys can all ask the same question. Well, you already told me, right? They're getting ready, they're going to move. Maybe they're just imagining themselves moving. So we brought back a new set of participants who had not done this experiment before. We put them in the scanner, and we asked them simply to listen to these rhythms. And this is what we found. That very similar cortical regions and regions of the cerebellum were active when people were listening to these rhythms and they had no intent to move. So what this tells us is that those motor regions and perhaps some of those subcortical basal ganglia regions are active when we listen to a musical rhythm, even if we have no intent of moving. So this tells us about that part of motor regions being engaged in musical timing, but it doesn't tell us about that component of pleasure. Why is it that when we hear those rhythms, not only do we feel the urge to move along, but that is a very pleasurable feeling, right? You only need to go to a wedding, and when people put on some kind of dancing music, you know, everybody gets up, from little children to grandmas, right? It's very pleasurable. So the way we decided to look at this is to look at this concept of musical groove. And this is an idea that was first talked about by Peter Janata. And what he did is he asked people to listen to a whole series of musical pieces, little excerpts, that come mostly from American soul and popular music, and to tell us, to rate for us, how much pleasure does it give you and how much does it make you want to move. And he really, so first defined this construct of groove that combines pleasure and wanting to move. And he'll see there are a couple of these songs in here that some of you might recognize. I think particularly Lady Marmalade that Christina Aguilera did. Many people's favorite, Stevie Wonder, Superstition. You can all imagine dancing to that. And there are lots of examples from, as I said, things like hip hop, soul, but also you can think of more traditional types of music, like perhaps the tarantella here in Italy, or salsa music, or other types of music. And we'll talk about, well, what makes them groovy? So I'll just first say, too, this is work that was done with Peter Wust, with my PhD student Thomas Matthews, and Maria Vitek. So what is it about these particular pieces of music or music like that that makes them groovy, makes you want to move? And what we think is that what makes them groovy is syncopation. So music that has a rhythm that is not 100% regular is rated overall as giving you a stronger feeling of wanting to move and a stronger feeling of pleasure. So this is telling you how syncopated is the music. So this is very little syncopation. This is very high syncopation, so very complicated rhythms. And what you see is this U-shaped function where rhythms that are in the middle, that have a certain amount of syncopation but not too much, are rated as more pleasurable and generating a greater desire to move. So what is it about syncopation? So I'm going to give you just an example, if you don't mind playing it. That's great. So you can hear this is a moderately syncopated, this is like a clave kind of Brazilian rhythm. And what you can see is, if you look at the notation, is that here is the predicted beat point here. And a syncopated rhythm has points in the music where there's no sound on the beat point, where the prediction is not 100% easy or obvious from the sound that's coming in. So what we think is that in very, very simple rhythms, like if you think of a children's kind of music, there's no syncopation, so your ability to predict what's coming next is kind of perfect. It's 100%. So there's no error, there's no surprise. You don't need to engage your motor system because you know what's coming next. It's completely predictable. There's nothing to learn. There's nothing new in this pattern. And that means there's no reward, there's no pleasure. So learning is itself intrinsically rewarding to us as humans. So when there's deviation, we want to learn from it, and there's a reward there. If the rhythm is too syncopated, if it's too unpredictable, and I'll give you an example in a moment, you have extremely poor ability to predict. You can't tell what's going to happen. So if you think of some crazy jazz piece, right, you can't tell what's coming next. Or it's one of the problems that some people find with very contemporary music. They can't tell what's going to happen. Very poor prediction. It means that there are lots of errors. You're making lots of mistakes because you're trying to predict, but it's uninformative. It doesn't help you figure out what's going on. This generates less urge to move, lower learning, little pleasure. So the idea is this medium, syncopation is that sweet spot, right, where you have a moderate ability to predict. You can make a prediction. There's error, but it tells you something. There's surprise. It generates this urge to move. It gives us pleasure. So now what we did with this is we wanted to look at where in the brain, or can we see these regions of the brain that we think are important for both pleasure or reward and movement in this experience of groove. So we know from previous research, particularly from the lab of Jessica Gran, that these regions that I talked about before that are in the dorsal auditory stream and these basal ganglia regions are active when people listen to rhythms that have a stronger musical beat. So here we see the basal ganglia, but also premotor cortex, SMA, and the auditory regions. Further, we know from the work of Valerie Salimpour and Robert Zatori that regions that are engaged in that reward network are active when people hear music that gives them the chills. So some of you may have this experience when you hear a piece of music, or you hear, usually it's a certain section in a piece of music, and you can get, tingles in your spine. You might get slightly sweaty fingers. It's a peak pleasurable experience to music. And what you see in those studies is that regions of this reward network, particularly the ventral striatum, are engaged when people have this peak chills experience. But also the putamen, remember I said that this links to the motor regions of the brain, and the caudate, which link to the frontal cortex. So what we did is we looked at rhythms that were either moderately complex, so like that one that I just played, if you don't mind playing it again. Right? And then we compared it, if you can stop that one, and play the next one. And that's good, thank you there. So that second one you can hear, you can make some predictions, but it's much more difficult to follow. So we called those moderate complexity rhythms the high groove rhythms, and we compared them to those more complex, less groovy rhythms. And we did this with musicians and non-musicians, and we also measured their, the activity of their brains when they were in the scanner, and we asked them to rate how much pleasure did they get, and how much did these rhythms make them want to move. So fortunately, for us, we were able to see that those medium complexity or medium syncopation rhythms were rated as higher in both wanting to move and pleasure than these higher syncopation rhythms. And what we saw in the brain is that if we compared activity between these high groove and low groove rhythms, what we showed is these same regions of the motor cortex, so supplementary motor area, premotor cortex, and the basal ganglia were all active for these high groove rhythms. But we wanted to know a little bit more about these specifically reward-related regions in the basal ganglia. So what we did is we identified these regions, so broke down this area into ventral striatum, putamen, and caudate, and we looked at the relationship between the activity in those specific regions and rhythmic complexity. And what we saw is that for the ventral striatum, so this reward-related part of the basal ganglia, again, it was higher, activity was higher for these medium syncopation or high groove rhythms. But the same was really the case as well for the putamen and the caudate. So next, what we tried to do was to look at the relationship between activity in these particular regions and the ratings that people gave. And what we saw is that for the ventral striatum, this reward-related area, the activity in the region was more related to pleasure, to ratings of pleasure, and that for the putamen and the caudate, activity was more related to the experience of wanting to move. So what this is telling us overall is that both motor and reward-related regions are engaged by these groovy stimuli, and that we have some evidence for dissociation between these ventral striatum regions and the experience of pleasure, and these more dorsal regions of the caudate and wanting to move. So I can see that I've got exactly 36 seconds left. So what I'll say is that high groove rhythms generate an optimal rhythmic prediction that engage motor and reward networks, and they drive both pleasure and wanting to move. And that we think that these different Subcircuits are important for different aspects. So this more motor circuit related to representation of the beat, this more frontal cortex region circuit related to metrical predictions, and this circuit between the ventral striatum and the orbital frontal cortex that monitors and assigns affective value. Next steps, we want to think about whether these are separable percepts, how are they experienced in the body, think more about groove and dance. And I'll just stop here and thank all of my collaborators, the funding organizations, and I'll thank you for your attention.
Thank you, Virginia, for this fascinating talk. So I learned that during music perception, there is a short-term memory system that is going on and that makes you predicting what will come next. So this is an engagement into the future. So we are doing mind time travel whilst we listen to music.
Yeah, maybe I wouldn't think of it in terms of time travel. I would think of it in terms of you have a representation about musical structures that you've learned from your experiences in your musical environment, and you use that memory, that structure to make predictions about the music that you hear coming in. Yeah.
Thank you. One quick question, I'm sorry.
It's my fault. I talked too long. I got too excited.
But Virginia, again, as all speakers, is around. There is a coffee break, and after we shall, if we have time, we can take questions again.
Yeah. Do you think that intrinsic body rhythms, such as heartbeats, can play a role in the perception of groove and musical pleasure in general?
I think heartbeat is not something I know about, but people think that intrinsic rhythms, like the rhythm that we walk at. So if you look across cultures, the common beat rate is at approximately 2 hertz, which is around the rate of walking. And it makes a lot of sense because we probably think that evolutionarily, rhythms were generated either by dancing, stomping, hitting an object, and so it's going to take into account the physical constraints of your limbs, which move at about that pace. Yeah. So I will stop here.
Thank you very much.